let's try to see what are the protons that are in chemical equivalence of the compound in my blue square. So we are expecting, so this CH3, this CH3, and this CH3 is going to have the same peak because they are in chemical equivalent. This hydrogen, and this hydrogen is going to have the same peak. Okay, so here is where the yellow hydrogen falls in, and here is where those blue hydrogens falls in. Okay, so later I'm going to show you the real spectrum of NMR, which looks a lot more different than this simplified version. For now, the reason that we give you a simplified version is to let you guys know there is a peak. The only thing we want you to know is there is a peak. But as you can see here, there are different number of protons, and that's going to affect the integration. Okay, so that's the first concept that you need to learn today, integration, which means it's the area. So it's the area, and area is usually the width times the height, right? So times the height. Since the width of each peak is going to be really similar, we sometimes use a ruler to measure the height of the proton. And that's going to tell me a general idea of how many protons are there in the peak. And this is height 1. And you can tell that height 2 is equals to 3 times of the height 1. There are 3 times of the number of protons in this peak, in the peak around 2, than the numbers of protons in the peak around 7. Also, this is a good example to show you that although it's writing 1 proton here, in reality, this is 3 protons because we all know this 3 hydrogen is chemical equivalent and they should fall in the same position. This one is going to be the 6th proton here. That's it. This hydroxyl group is here. We can tell from the shape. I just randomly use a color to write. Okay. So it's one of those peaks that I'm highlighting here between 7 to 8 is the hydrogen on benzene. So only if you are pretty sure that this peak, this integration is 1 proton, then you can compare the height of this one, and this is height 2. Okay, the height of that. So height 2 equals to 6 times of the height 1, and I'm pretty sure there can only be 1 proton in my height 1, then the peak around between 2 and 3 is going to be 6 protons. That is showing an example here. This 2 proton is and it's also the 2 proton on this side. So in reality, this one should have 4 protons. So this is the CH3. So that's the CH3. But because of the symmetry here, there is also another CH3. So this one in reality, there's 6 protons. But when you just measure the height or just measure the area, the only information you can get from the integration in this part is 2 to 3. But you don't know if that's 4 to 6, or it might be 6 to 9. The next topic would be coupling, spin, splitting, okay? Previously, all of the peak that we choose, we meant to choose the peak that won't be affected by other peak, which means by your neighbor. But keep in mind, everything in NMR is all about magnets, which means as long as there are electrons around you, it's going to make a difference. So previously, when we were trying to assign R and S, the neighbor we talked about is just the carbon next to you. But now, since we are going to talk about the proton NMR, this HA and HB, they are neighbor. The neighbor doesn't mean it's bonded to the same carbon. It has to be the carbon next to you. So the proton on this carbon, carbon 1, and the proton on this carbon, carbon 2, they are neighbors. Okay. So is the hydrogen A and hydrogen C neighbors? They are not. So because there is a carbon in between. So what we are going to talk about here. So from now on, if we are going to talk about neighbor, then it's the relationship between HA and HB. Okay, here, let's take a look at what would happen. If I'm just alone, so for whatever peak that I'm assigning to, so RF of HA, let's just say, for example, it has the peak around 2.1. I just made a number for now. So previously, if it's just myself and I'm applying a B naught magnet into HA, it's going to give me a peak around 2.1. But now, if I have a neighbor, HB, here, what would happen? Because HB, there is also a small electrons in my HB, and that electron is going to have either alpha or beta state. So it's either going to spin up or it's going to spin down, like this. And since everything we talk about here is going to be related to magnets, and that small magnet, since we're close enough, since we are neighbors, since we're only 3 bonds away from each other, this HB is going to affect my 2.1 significantly. Well, not significantly, at least from our magnets, but I can see that. So let's say if it's spin up, it's going to add it to my B naught. So the B naught, it's no longer the original B naught, it's the B naught plus my B1, which is generated by this HB in around 2.0. Similarly, minus a peak around 2.2. That's originally what it is. So instead of the real 2.1 that I'm expecting on a real NMR spectrum, what I'm going to see is actually this 2 peak. Okay, so we are not going to see the green peak in the middle. So there's a distance between these 2 peaks, right? We call this J coupling. This 2 peak that has been separated by my neighbor proton B, HB, we give this distance a name, which is J coupling. So this is coupling constant. So the distance, so it's the distance between the split peaks, and usually is measured in hertz. We use a letter J to describe the distance between these split peaks. N+1 rule, summarized by the previous people. We just talk about what if I have one proton neighbor. In reality, if you have more than one proton neighbor, you're expecting to see different kind of J coupling, different kind of the shape of the peak. So this is the example that we just talked about. That if I have one proton neighbor, so we are always focused on HA. So HA is the only peak that we are focused on. So if I only have one neighbor, because this neighbor is going to spin up and spin down, and that's cause my HA to split. So this is a doublet. So there is a name D. Okay, doublet. We use a letter D to describe. Of course, if it's on its own, it's a singlet. So that's where we use S to describe that. Okay. What if I have 2 neighbors? So proton. So each of them is going to spin up and spin down. Then it's going to cancel the extra B1 that each proton has been applied to my HA. In this case, although my peak was still remaining in the original position that I'm expected to be as originally, if it's alone, the integration is going to change. It's the probability. So let's say because there are twice amount of the probability that's it's spin up, spin down. So we count it here. I'm expecting to see this integration to be higher than both spin up or both spin down. So sometimes the J coupling between each peak is going to be really small, and you cannot really tell if this is a triplet or not, unless you are really familiar with the shape of that. If I have 3 protons, I'm expecting to see there are more combinations of that. So see, because my 3 protons cannot cancel out, it's always going to have an extra one. So I can no longer see that original peak according to their populations. I'm also expecting the area of this peak, so the pink peak that I'm pointing at, to be 3 times of the yellow peak that I'm pointing at. So this is going to be 1, 1, and the 2 in middle is going to be 3. The ratio of the area under each position to be 1, 3, 3, 1. So whenever you see something similar to that, portrait. Similarly, you're going to see hand pick. So I'm not going to go through each of them then. And then there are more number for you to memorize. It's always going to be one more pick than your neighbor. So N is your neighbor. So you can see if you have one neighbor, you're going to see 2 pick. 2 neighbors, you're going to see 3 pick. 3 neighbors is going to be 4 pick. 4 neighbors is going to be 5 pick. Right? So you're always expecting to see one more pick than your numbers of neighbor. Okay, and this, let's emphasize what are the neighbors again. The neighbor has to be the proton bonded to the carbon next to you. Okay, so that's your neighbor. So if I have one more carbon here, and there's a proton, is that proton going to affect my HA? At your stage, it's not. Okay, in reality, we need to discuss the exact scenario. Sometimes it might still affect the HA, but now at your stage, it's no. So only the proton next bonded to the carbon next to you that is going to affect your magnet. Practice on GHLK. It's the same molecule that we practiced on Monday. Okay, let's get started. The first one, so compound G, we talk about there is a symmetrical plane in the molecule. So I only need to count on one side, and that's why we only labeled A and B. Okay, so if you still remember that we have talked about the wedged hydrogen and the dashed hydrogen. We talk about these protons are dirostereotopic, so they should have different peaks. Similarly, because it's symmetrical, so I'm also expecting there is going to be a pair of similar protons, and both yellow protons is going to show in the same position. And there is a hidden dash hydrogen, neighbor 1, neighbor 2, neighbor 3. So number of peak 3 plus 1 equals to 4. So compound G for A, I'm expecting to see 4 peak. And for B, I'm expecting hydrogen, the green hydrogen, to be its neighbor. For signal B, there is only one neighbor according to our N plus 1 rules. So B, I'm expecting to see a doublet peak. A is going to be a quartlet peak. B is going to be a doublet peak. And compound H, what is my neighbor? Magenta carbon is the neighbor carbon that my proton A has. And this one has 2 protons, hydrogen A with magenta. So A, the number of neighbor is 2. And I'm expecting to see 2 plus 1 equals to C, equals to 3 peak. Okay, so A, 3. And the name of a 3 peak proton is a triplet. B. Okay, B. B means the 2 proton here, and different from the proton on a ring, that these 2 protons are homotopic and they should have the same peak. But let's count how many neighbors that it has. So the neighbor has to be the carbon next to the carbon that my proton is bonded to. So here is a hidden proton. Here is a CH3. So for proton B, that's I'm expecting to see 4 neighbors, right? So according to N plus 1 rules, that's there is going to be total 5 peak that I'm expecting to see. Okay, so we use letter P or penta to describe 5 peak. So compound K, A is a CH3, and this carbon has 2 protons. A, the number of proton is 2, so I'm expecting to see 2 plus 1 equals to 3. B are the proton here. Okay, so what are my carbon neighbor? So B has carbon, this deep purple, which doesn't have any hydrogen, because purple, this deep purple carbon is already bonded to 4 things. Then the only possible neighbor that it has is this light purple carbon, and there is a CH3. So for proton B, what I have 3 neighbors, and I just need to use my n+1 rules, plug in into the equation that B is going to be 4p, and this is quartet. Compound L, what are my neighbors? So carbon neighbor 1, which doesn't have any protons, so there are 0 protons on this carbon. Carbon neighbor 2, so there are 2 hydrogen. My proton A has 4 neighbors. Hydrogen A has 4 neighbors. Which are those neighbors? Okay, and according to n+1 rule, there should be 5. A, 5 peak, pentapeak. B, my proton B is only bonded to a oxygen. There are no carbon neighbor, which means it's going to be a singlet, 1 singlet. The real kind of question that we are going to ask you is interpret an NMR. A quick look at what's our expectation for you finally. Is we're going to give you an NMR spectrum and an IR spectrum. You need to write the structure for me. So previously we just assign. So if I have the structure here, do you know if this 3 peak is the meso peak here? So that is going to be a matching game. Here is a solving puzzle of both NMR and IR. That's our final expectation. Although we're going to talk about that in discussion 8. Very quickly after we talk about that, you're going to have your midterm. But it's not going to change the fact that it's our expectation. So you can go ahead to start work on those. And I'm going to teach you how I'm going to solve the puzzle on next Monday. The reason I ask you to do so is there are thousands of ways to solve an NMR spectrum. And you can choose the ways that you want, as long as your structure solved by the spectrum is correct. Because there is only going to be 1 correct answer for each spectrum that we given to you. As long as you can find that structure, I don't care how you are going to do it. The way that I'm going to introduce next week, it works best for me. So any questions about discussion this week? So you can see it's not very hard. For this week, we just expect you to know if you have a neighbors next to you, and it's going to affect the shape and the integration of the peak, and even the position, even the exact number of the position that you're expecting to see the NMR spectrum. So there's a huge gap from the expectation from this week to next week. I'm not expecting everyone can solve a puzzle immediately, but work on that from now on. So questions. Okay, there's a question. Can you explain how you did the ratios? Yes. So the question 3. Let's just take compound K for an example. Proton A, CH3, CH3, CH3. So keep in mind we talked about last week that this CH3 are in chemical equivalence. So I'm expecting to see 9 protons. There are 2 hydrogen, 2 hydrogen, and 2 hydrogen. So totally I'm going to see 6 yellow hydrogen. The peak that you're going to see on the NMR spectrum is at the shift of let's say 1.0 ppm. And the shift that you're going to see on the 6 protons is going to be 1.2 ppm, just for now. I'm expecting to see a peak with 9 protons, and I'm expecting to see a peak with 6 protons. So this is 6 protons, let's say 6 protons, and this is 9. So it's asking you the ratio. If I don't tell you there are 6 protons in the yellow and there are 9 protons in the pink, the only information you can read, let's say if we didn't give you the structure, is you're going to measure the height here, it's going to be height 1 and height 2 here. Let's say height 2 here. The only information that you can read is height 1 to height 2 is 2 to 3. only after you solve all the puzzles, then you figure out, for example, if we're just going to give you the compound, give you the formula of the compound, usually that formula is given. So you check the formula and you find that they're going to be, so this is a 15 proton, right? So you check the formula, it's going to CN hydrogen 15. There's a chloro, so chloro something. So there's totally 15 proton. Then you start to think, why I'm only going to see 2 groups of peak, and they have a ratio of 2 to 3. Then you start to think, maybe in the 2 that I'm measuring here, although it's a ratio of 2 to 3, actually there are 6 protons and there are 9 protons, so they added up to 15 protons. So that's why we ask you to exercise on the ratio, because you won't be able to see how many protons exactly in the height until you solve the puzzle. Okay. So you have seen this one since the first discussion. So I told you it's going to get, since it's going to get harder from now on, and started to make flashcard, you're going to see that this is actually 2 to 5. So flashcards 2 to 5. So it's not too late if you haven't started one. And trust me, it's going to be helpful. So you can imagine what I'm trying to do here. This is the flashcard. So this is the flashcard. That's the only difference is I'm trying to write the flashcards on a screen. There is going to be a good leaving group. So here, the first thing you need to know for all those substitution and elimination is it all happens to hollow alkyne, and usually there is going to be a good leaving group. So this is leaving group, okay? And the first step is you need to identify if this is a good leaving group or not. If it is, then we start to check if the condition that has been given is a good nucleophile or not. So I'm just telling you this is a good nucleophile, and we are going to separate those things out. A quick recall, this is non-metal. So non-metal. And sodium is metal. It's ionic bonded between these two. So we are going to write OET minus and sodium plus because they are ionic bonded. It's going to form a formal chart if you want. And what would happen to that is this nucleophile is going to form, it's going to attack from the back of the model. Okay, it's going to attack. So I'm going to use a dash line because you're going to see this staggered as transition state, which means I'm slowing down. I'm going to put a puzzle. So this one means transition state. So TS means transition state. Okay, and when the centric carbon in the middle has been attacked by the nucleophile, the leaving group wasn't really falling off yet. So at this stage, my carbon is partial positive, my leaving group is partial negative, and my nucleophile is partial negative. Okay, so there is a transition state that's nucleophile. And let me just use, I'm not in the campus, so I didn't bring my model back. So previously, it's just my hand is the centric carbon, and my pen is the leaving group. So it's a process of my nucleophile is attacking from the back of the carbon. And there is a transition state where both leaving group and my nucleophile are bonded to the same carbon. And the next second that of the transition state is the leaving group is going to leave. So if I'm going to write the mechanism, if I don't want to write the transition state, it's going to be this. So what would happen to that? Because I'm attacking from the back. Previously, my bromo is wedged out. So my nucleophile, which is OET in this case, is going to be dashed in. So it's dash, back attack. So it's always, so this is the only answer. So that's the only answer, back attack. And it's always going to change the R and S. So if previously the reactant is R, then this one is going to be S. Just to save the time for now, we are not assigning R and S. But there's a quick, easy way to think about that. Would it be previously your leaving group is wedge, then no matter how you're going to draw, that's your nucleophile is going to be dash. While SN1, that you have learned before. If you are watching the video, I hope you can post the video now and then practice on your own. Even I just give you the correct answer of what the mechanism is. I still hope you to practice on your own. But just to save the time, I'm just going to go through it. In SN1, it's different from back attraction. The first step would be leaving group leave. So my bromo is going to leave first. And this is based on the fact that this center carbon is going to form a carbocation. So you must have seen this word. So carbocation. And it's not carbocation, okay? It's carbocation. This carbocation has to be stable enough. And she mentioned about tertiary is going to be stable, more stable than secondary, than primary. This is a secondary. How do you know it's secondary? Because it's bound to 2 carbon. Okay, that's secondary carbocation. It's still within the tolerance of how stable a carbocation can be. That's this mechanism is good to work with. If this site is a proton, then this is going to be a primary carbocation, and this mechanism would stop here because primary carbocation is really unstable, and she's going to emphasize that a lot more in tomorrow's lectures. I just bet that it's going to happen. But for now, it formed a secondary carbocation. What else is going to happen? Since I have a nucleophile, my nucleophile, a quick reminder, because both ETOH, all of them are non-metal, you cannot write in a way as we did before. So here, ETONA, you can write in this format. Now, ETOH, you cannot. The most common mistake I see in the exam is someone is going to write this to me. So it's not happening. It's not happening. ET is all covalent bonded. So the whole ETOH is going to attack as a group. So you cannot write a formal positive charge or formal negative charge if it's all covalent bonded. So what would happen to here? Because I can attack on both front and back side of my carbocation. What do I mean by that? So previously we talked about if it's at sp2, which is the carbocation, the center carbon, they are on a plane. So just imagine it's still my pen, that is the center carbon, my hand, my Apple pencil, and my pen. They are the center carbon. And my nucleophile can attack my nucleophile. Let me just find a nucleophile. Okay, my nucleophile can attack from the top or can attack from the bottom. So you are going to have 2 different results. Let me just copy paste these 2 first. Okay, so one of them is going to, let's say this orange one, then it's going to be OET hydrogen. So we use a 1 pair of lone pair on my ethanol, on my oxygen of ethanol to attack. That's this oxygen is bonded to 3 things. So 1, 2, 3, right? So it's bonded to 3 things. Then this oxygen is going to form a positive charge. Common mistake would be starting from a wrong lone pair. So you have to start from the lone pair from oxygen. Don't start the arrow from ethyl or hydrogen, okay? And leave my previous hydrogen wedge, or the other way of that. So it can be, and my original hydrogen was dash, okay? So these 2, so far you should be familiar with. These 2, what are the relationship between these 2? There are only 1 stereocenter, and the only stereocenter are opposite to each other. So we talk about as long as all of the stereocenter are opposite to each other, they are a pair of enantiomers. Otherwise, they are diastereomers. Okay, there's a question. Which one is back attack and which one is front attack? It doesn't matter. You just need to know there are two different molecules. And then the next step would be a Lewis base is going to grab the hydrogen and return the lone pair to oxygen. So it's going to form Lewis base with a hydrogen. And I'm going to proton disappear. And finally, my products would look like this. So this is SN1 and SN2. We talk about SN2, there's only answer because it's always going to be back attraction. SN1, however, is always going to be a mixture. As long as you can see couple cation is forming, then it's always going to be a mixture. She also talked about E1 and E2. The things that you should keep in mind for E2 would be the leaving group has to be in the anti-position of the hydrogen that you are trying to draw. So what I'm doing is I'm to rotate this chloro, and I want to make this wedge chloro into the position, anti-position of the hydrogen that I need to draw out. So the reason that I'm trying to choose away from this. So previously, as you can see here, previously my methyl group, so CH3, previously my methyl group is in a solid line, but I always ask my students to do a rotation. Use your hand as the model to do a rotation and to put the leaving group in the solid line, in the plane of paper. So it's going to be more clear for you to see where is the anti-hydrogen, okay? So similarly, there is a dash hydrogen as well. Okay, so I'm going to highlight this one. So CH3. So this CH3 is here. So I meant to rotate them into the anti-position that you can actually see this chloro is in anti-position to this hydrogen. And that's the condition of E2. That's if you want to make E2 happen, you have to have an anti-position hydrogen to your leaving group. So when you are writing the mechanism, one of the points that you are going to lose easily is you forgot to write what has been fall off. So for example, here, the chloro is fall off, right? That's the leaving group. What else? So also the HOCH3 is falling off. So what you are forming is going to be, because sp2 doesn't have wedge or dash, sp2, keep in mind, if it's double bond, it's all in the plane. Okay, so this is the previous CH3, and this is the previous CH3. Okay, I didn't draw the hydrogen. So previously this was a dash hydrogen, but now it's just a solid hydrogen. Okay, so that's our compound. That's E2. E1. So the first step of E1 is going to be similar to SN1, and it all requires ET. It all requires leaving group leave first. So what would happen to that if my leaving group is leave? So don't forget to write this one, okay? So it's going to form a carbocation. So I'm write the one of the acyl group out because I'm going to use the hydrogen on it. So on my so there is a positive charge as well. That's the carbocation. So on my hydrogen here, so there is one hydrogen, there is another. So what would happen would be my nucleophile HOCH3. The lone pair on my nucleophile is going to grab one of the hydrogen and form a double bond. So by doing this, the whole thing is going to fall off, right? So it's going to be CH3OH2 plus ET. So there is a hydrogen and a methyl. That's what's the previous hydrogen. So I just quickly go through all of the 4 mechanisms that you are going to see. So I probably need to continue this part on next Monday. For this kind of question would be, first, you need to be very familiar with each condition. Second, and on those conditions, how could I make the correct choice? Which comes to this part. So this is the logic. So the parts right here is the logic. Why this is the major reaction and what I'm considering between these two. So you can go ahead to work on this on yourself. So I think that's the end of this discussion. Okay. Bye bye.